Alrighty. Happy Monday, folks. A little slow today. I apologize. It's been quite the weekend. Did the marathon. It was my worst one ever. Got really sick, but I finished anyway. And then my brother's car got stolen from Eastern Market, but we found it later at a gas station in Highland Park. It was a day. They went through his glove box, and that was it. So, I mean, probably the best outcome that could have happened from having your car stolen in Detroit. Really just weird day. But next year will be better. And we'll have a better run next year is the plan. What is this? Fun page. All right. We got a couple things today. Moving on to lists and dictionaries. I'll spend a little more time talking about the strings lab as well. I had lots of questions on that. So spend a little time with that one too. Let me start a new project here. String lab or something. Call that. That's probably fine. So we looked at a quick example in class of going through some of this slicing idea here. All right, so the idea with our encrypt function, encrypt given some string and some stride. You give me the string, you give me the stride. We say, well, based on the stride, we need to make so many chunks. We could say for index in range stride, we need that many chunks, right? And that happens to be the starting character as well. So we'll have our encrypted string. Probably should start with the value, right? Just empty for now. And then we can take our encrypted string and we can add to it the string starting at the index, sliced to the end, at a given stride. So this will make stride number of chunks, starting with the first character, that many characters, starting with the second character, that many characters, starting with the third character, that many characters, for whatever stride I want. Right, it's very flexible. And now we've scrambled the string at this point. Encryption's probably still even the wrong word for what we're doing here, but we're going to scramble and then we're going to encode. Right, so taking advantage of the slicing does all the hard work for us. We could do it differently. Like we could go through loops and grab one character at a time and make sure we don't go over the end when we start adding stuff. But like just giving it the default ending location here means it will go to the end for us. We don't need to figure out where that end location is, which is nice. So when we talk about strings and all the string functions, like we can do all of them by hand, essentially, one character at a time if we really wanted to. We really don't want to do that though, right? We want to make cool stuff with the code that's already written, right? We don't want to have to reinvent the wheel, right? Then we're going to go through for index in range of the length of the encrypted string, right? Because we need to get that index value out to get the individual character, grab the ordinal value, add the index to it, turn it back into a character. So really, this is probably not even the encrypted string. Well, the encrypted string, maybe this is like the scrambled string. This is probably a better way to call it here. And then I'll go back and do the encrypted string because we want to add characters to that. Right? We can't change characters midway through. So we'll build the scrambled string and then we'll build the encrypted string. So we'll take that, we'll add a character to it we're going to create a character out of the ordinal value of the scrambled string at the index. That's the ordinal value, right, of that character plus the index. So take the ordinal value of the character at that location, add its index value to it. So character at index 0 doesn't change. Character at index 1 goes up by 1. Character at index 2 goes up by 2, and so on and so on and so on. If we're done, we can return that encrypted string. Right? I think we got pretty far with that on Monday last week. Going through some of this, but we left the decrypt for later, right? But we could test that, right? We could say let's print the encrypt. We said, hey, if I just give it 5 A's, right? And we said, oh, I guess the slicing here is kind of silly then. So if we do A, B, C, D, E here. So it's 5 characters long. So we want to stride, let's say, every 2 characters. So we should get A and then C and then E, getting every other character. and then we should get B and D. So like the intermediate step here then is A, C, E, B, D. And then as we start adding the index here, A doesn't shift, C goes up by 1, we should get a D, E goes up by 2, we should get a G, B goes up by 3, we should get C, D, E, no, C, D, E, and then D goes up by 4, we should get D, E, F, G, H, H, right? That makes sense? I'm talking a little fast. I'm compensating. I had a lot of coffee. I'm on to Coke already now because 3 cups of coffee is not enough in the morning anymore, at least after yesterday. Maybe a normal day, 3 is enough. You just holler me and tell me to slow down if it's not making sense. So we should hopefully get out A, D, G, E, H if we did this right. Look at that. A, D, G, E, H. You guys are impressed, right? I'm impressed it worked. I thought I would do something wrong. Okay, now to decrypt it, right, we need to reverse that process. So we write a function for decrypt, given a string, given a stride. Right, we're going to reverse this one first. Right, we need to go from the encrypted string to the decrypted to the scrambled string, and then we need to go for the scrambled string back to the original string. Right, so this is the decrypted string. Sure, why not? Given the string, the string, and the string. Right, so instead of adding to the index, we're going to subtract the index. So this will go from I've shifted all the letters up by the index to I've unshifted all the letters up by the index. Now we need to go and unscramble. So maybe we'll call that the encrypted string. I like that. We'll call that the encrypted string. And this is our decrypted string. How about that? Okay, and then we go back to a string here, or original maybe. Original is just an empty string. Now this one gets a little trickier, right? Because we need to take the right number of characters for each given stride, right? So when we scramble it up, we said, hey, when I took every other character, how many were in the first chunk here? Right? How many could we fit? Well, it's based on my stride, and it's based on the length of the string, right? So I could say, take, I don't know, for index is 0. Nope, sorry, because we want to go, we want, how about we'll use a while loop. So we'll say, hey, index is, okay, I'm sorry. So for index in range stride, right, this is the starting index. So as many strides as I have, right, we have this many starting indexes here. So I'm going to take this index and I'm going to see how many times I can fit it into the word to know how many characters to take for that chunk, right? Because I'm going to take, I want the first 3 characters, right, need to be put back in the right place, and then the next 2 characters need to be put back in the right place. So we're going to build out a bunch of chunks, right, and kind of put them back in order, right? So we probably need a bunch of chunks. There's maybe a list here. Can we do that? And then we're going to go through and start rechunk. So we're going to rechunk the scrambled string. Right. So for the first stride amount, then I need to get so many characters. So it's going to be how many times can I get from 0 up to the length, counting by this number. Right. So I was able to get 0, 2, and 4, right, out of the 5. And then I could get 1 and 3 out of the 5. So I'm going to have to be less than. There's got to be some easy math here. I'm trying to think of what that math is in my head right now. But I have the length of the decrypted string is going to be 5. And I want how many times can I get 2, counting by 2, starting at 0, to go into this. Right? Guess we just need, what do we want to do? We can just do a while loop, I guess. So we'll have the Index is the chunk number. I want to use index. Wow, I'm sorry, my head's hurting right now. I want to take the right number of characters out. Grab 3 and then grab 2. All right, so we're going to start at the index. Okay, so this is our, so the index will be where we're starting, right? The value we're going to start with, and then we're going to see how many we can count out. So our count of characters in stride, right? We'll start at 0, and I guess we don't really want to change index. We'll say current index is equal to index to start, and while my current index is less than the length of the decrypted string, we're going to take our current index, we'll count a character. So if the current index is less than the length, we count a character, right? And then we'll take our current index and we will add to it the stride. Because if we're getting every other character, we'll add 2. Can we still grab a character? Sure. Can we grab a character? Sure. Can we grab a character? Sure. Right? So this will find out how many characters I need or will fit that I would have gotten out of that original stride. When that one's done, then I can go and grab the chunk. Right? So I know I know what my count of characters in the stride was here. We probably need another current stride chunk start. It's going to be 0. So we're going to grab our original string then, and we're going to add to it. We're going to grab a slice of the decrypted string from index of the current stride chunk start, going up to the count of characters in the stride, plus 1, right? Because if I have 3 characters in the stride, oh no, that's right. Okay, so I don't even need a plus 1. So the count of characters in the stride will be the number of characters I need from the current stride chunk start. I need my decrypted string. So we're going to take a slice of the decrypted string, starting at where our current stride chunk started. So at 0, great, we're going to take a slice from 0 to 3. Right? Then we need to go and set our current stride chunk start to the count of characters. Or no, we're going to add the count of characters to it. Right? So then 0 goes up to 3, and we go back here. Now our index is 1. Count of characters in stride goes back to 0. Our current index starts at index of 1. So while the current index is less than the length of the decrypted string, let's see how many times we can count up. So starting at 1, is 1 less than 5? Yes, we have a character. Is 3 less than 5? Yes, we have a character. Is 5 less than 5? No. So we only have 2 characters here. Okay, so we'll get our original, we'll add to it the decrypted string starting at 3, going 3 plus 2, going up to 5. We'll take the next chunk of that, right, and add it to the current stride chunk start. Oh, I guess we don't even need the chunks then, right? We're just building out the original. Okay, I think that works then, right? Because we can build out the original string. So we're done. We should be able to return the original string. So if I take this string and I print a decrypt of that with a stride of 2, we should get back A, B, C, D, E. Hopefully. Oh, it's close. It's close. Oh, we didn't. That's right. That's why I wanted to get these. So I did want to add them to chunks. I'm sorry. So I don't want original yet. We want chunks because we need to put them back in order next. So chunks is this list. So we'll take chunks and we'll append this value here. Right. Then I can put them back to the original string. Original. So I need to start looping through every chunk and get back to my original string here. So actually, I don't want to loop through the chunk. I want to just go for every chunk, right? For index in range, we want probably the length of the first chunk, right? Chunk of 0, chunks of 0. right? Because that'll be, I'll get the first index, the second index, the third index out of that one. So we can take, now we need every chunk, we're going to take a letter out of it, right? Starting with that index. And then we'll go through every next chunk and take that index letter out. And every next chunk, take that index out. So we're going to say for what character, no, for index, so that'll be 0th the 1. So for chunk in chunks, I'm going to take our original. I want to add to the original string here. Oops, original string. Decrypting is much harder than encrypting. Sorry about that. Original. Is there another I in there? I want to add the chunk at index here. But we only want to do that if the length of chunk of index is less than the length of the chunk. Because not all the chunks are the same size, right? So the first chunk has 3 letters, the second chunk only has 2 letters. So there is no index 2 in the second chunk, but I need the most possible letters here. So for every chunk in my chunk list, go through and grab the first letter. For every chunk in the chunk list, grab the second letter. For every chunk in the chunk list, grab the third letter, if there's a third letter. A, B, C, D, E. We've reversed it. This was a pain in the butt to reverse, I'm sorry. So now we should test out other strings, right? How about if we add an F? If we add an F, that turns into a K. F, that one worked. How about a G? Turns into an L. All right, that's working so far. How about we try with different stride lengths now, right? If we stride for 3, well, obviously it didn't unscramble right because we didn't have the right string in here. But now if we unscramble with the stride of 3, it unscrambles. So just a lot of steps here, a lot of steps, trying to undo the things that we did. So because this was so easy for us with string slicing, right? Like we said, we don't need to check for the end. We don't need to do all that. I'll post all this code after. Undoing this is the hard way because we can't just take a slice, right? Because we need to individually unslice it after we figure out what the right chunks were. Does that make sense? Going through it? It was a lot. I'm sorry. And I think it's a good illustration, and maybe I'm wrong here, of that. I feel like the hard part here wasn't the code. The hard part was, what is the step we need to do incrementally to undo this? And my head started hurting trying to figure that out, just on the fly here, right? The hard part of coding is, what are the steps I need to take in this big problem to make it a smaller problem, right? The code part, we're still learning the code, so yes, it's not going to be the easiest thing, but if we know what we're doing, then it's much easier to write the code. Right? If we don't know how to solve a problem, then we have got no chance of writing the code to solve the problem here. And again, I think I talk about this a lot, but I like the idea that coding really is an art. There is science to it for sure, but the art of problem solving is the hard thing that we're trying to learn. We're also learning the computer language so we can tell the computer to do these things step by step by step by step. But really what we're figuring out is, how do we solve problems? So like good developers, good data scientists are problem solvers. We learn how to solve problems with code. It's kind of the idea here. I keep looking at people who look at me. I'm sorry. I look around the room, and if you make eye contact with me, I will make eye contact back a lot. I'm sorry. Maybe I'll just stare at my camera. We okay? Sound good? Okay, cool. So let me go post all that here for lab. That was our string lab. Again, this was just a chance to exercise some of these string. I guess we didn't use a whole lot of the string functions, but the slicing is kind of the interesting thing here. Like uppercasing, lowercasing, those are kind of boring when it comes to strings, I feel like. All right, so we're moving on to lists and dictionaries. I think I was naming these by week, right? So I'd say week 8, lists and dictionaries. That sounds right. So we've done some basics with lists and we've done some basics with dictionaries. But now we're going to jump into using more of them, more of their cool features, other fun things we can do with them, which is really fun. So the whole chapter is broken up, kind of lists first and then dictionaries. Right, all the fun list things, then all of the fun dictionary things. So we'll start with lists today, see how far we get. Okay. So things we can do with lists, right? We've appended. You can insert a value at a given position, because remember with a list, it's a sequence type. The order matters here. I don't think have we looked at insert yet? I don't think we did. So if I have a list of I don't know, my lotto numbers, right? Lotto numbers. And I said, okay, let's pick some lotto numbers. Honestly, it doesn't matter the numbers you pick. It's still a random chance. So people who tell you they have lucky numbers are full of crap, right? We know better because we understand numbers, right? And we understand how probability works. So usually if people are convinced that numbers are lucky, you're not going to be able to change their mind. I've found, which is really sad. But human brains are super complex. And like, apparently if you tell someone they're wrong, it activates their fight or flight response. And like, if you're in a fight or flight mode, you're not really going to be listening to someone. You're just trying to defend yourself and run away. It's really crazy. So like convincing people is really hard to do. But we know the numbers don't really matter because we know how that works. So I can say, okay, hey, 1, 2, 3, 4, 5 is just as likely to come up as any other lotto sequence here because this is how numbers work. Smile, reference my code for doing the lab. If you just copy paste and turn it in, it's not a very good exercise. If that makes any sense for the lab, right? So if you haven't turned it in yet, that's okay. Work on it. But if you just copy paste, like, I don't know, I feel like you're not going to get a whole lot out of it. And the labs are meant for practice, right? That's the whole reason we have lab time is we can practice. I can walk around and answer questions. It'll probably turn out to be a mostly copy paste. So I don't know. If that's what you do, that's what you do. But at least make sure it makes sense for that. Because if it doesn't make sense, let me know. We can talk through it and go over the steps again. Because that's the goal here. All right, so we got lotto numbers. So if I wanted to add another number, I could take my lotto numbers. I could say insert. So insert needs two values. It needs what index do you want to insert at. So what index do you want to insert at, and then the value. So if I want to insert at index 2, right, make it the new where 3 currently is here, and add, say, 11. I'll now get 1, 2, 11, 3, 4, 5. So it's not replacing the value there, it's adding it, and it becomes the new index. So it becomes the new index 2. We can print my lotto numbers, and we'll see that we've now added something at index 2. So insert's really handy because we don't need to take everything else out, pull it all out just to add stuff if the order that we're putting things in really matters. Right? So if I wanted to, I could say, hey, let's build out a list of your lotto numbers equals a list. And I'm going to ask you, we'll say while number count, while length of your lotto numbers is less than 5, let's go ask for a number. We'll get a number, we'll get an int of an input, given, enter a number, excuse me. And then we can go, right, if we just wanted to append it, we could just append, they'd show up at the end. They wouldn't be in any sort of order. So if you want them to be in a certain order, we should put them in a certain order. So we'll get the number and I can check. I can say, hey, is it less than the value? Right, so I can say, hey, if the, I guess, the very first time it's going to be empty, right? So if length of your lotto numbers is 0, we'll take our your lotto numbers and we'll append the number. If it's not 0, then we have other stuff to do here. Right? If it's not 0, then I need to start checking, is it less than a certain number? So we can say for index in range length of your lotto numbers, if the number is less than your lotto numbers at the index, then I need to take your lotto numbers and I need to insert at the index the number. Right? If it's empty, that's easy. Just throw it in there. If it's not empty, then let's go through. We'll go find where it needs to go. As soon as it is less than something, let's put it at that spot. So if you're less than the first value, sure, we'll put it there. If you're not less than the first value, but you're less than the second value, right? Now you go in that spot. Right? We might go all the way down to the end and not have added anything, right? If we weren't careful. Right? So probably this might be a good case for the break here, right? To end the loop stops, we're done, game over. And then remember, loops can have an optional else that only run if you don't break. Does that ring any bells? The loop else clause here, it only runs if you don't break. I'm not getting a lot of head nods. I don't think we spent a lot of time on it. It was in Zybooks, if you read Zybooks. If you read Zybooks, give yourself a round of applause. I'm proud of you. Is there a question? Should what? Move what? No, the else is on the for. Loops can have an else. This is a loop else, not an if else here. So if you break the loop, the else doesn't run. If you don't break the loop, then I can just take your lotto numbers and I can append the number because we didn't add it at a given index. Right? So this will add 5 numbers and we'll add them in a sorted order as it goes, because when I have no numbers, it adds it to the start. When I have one number, it checks is it less than that one number. If it is, it goes at index 0, breaks. If it's not less than, we just append it. Loop is done. If I have 4 values in the list, right, we'll check the first value, we'll check the second value, check the third value, and on and on and on. So let's put this in debug mode here, because this is really fun, and we'll debug it. All right, so at the console, oh, sorry, we have to step one time there. Now it'll ask for a number. So what number should we enter? We're going to enter 5 numbers, any 5 lucky numbers. Make sure they're lucky. If it's not a lucky number, then we're going to lose our money playing the lotto, and we'll be sad. 13. Okay, so the number is 13. The length of lotto numbers here should be 0. So if I step, great, it's just going to append. Is the length less than 5? Nope, not less than 5. Okay, let's get another number. All right, we got a 13. What else should we add? 7. Okay, so our number 7, our length is not 0, so we're in our else clause. Now we're going to loop through the range of the length of lotto number. So the length is 1. When we range for 1, we only get 1 time. Index is 0. Right, so index is currently 0. Is our number less than lotto numbers at index? Is 7 less than 13? Yes, it is. So we're going to insert at index 0 that value. Okay, now our lotto numbers is 7 and 13. We break, go back to the while. Okay, are we less than 5 numbers? Yes, we are. Let's grab a number. What number now? 56. Right, we're not empty, so let's range through the length of lotto numbers. Now there's 2, so we're going to get 0 and 1. Right, is number less than your lotto numbers at index 0? Is it less than 7? No. Right, now index is 1. Is it less than 13? No, it's not. We're done with our for loop. The else runs because we didn't break. Awesome. So now we're going to append. We added 56 on the end. Right? Or do we have 5 numbers? No, we don't. Let's get a number. What number now? 42. 42. Right? It's not empty, so let's range through the length of lotto numbers. Now we have 3 numbers. We're going to do 0, 1, and 2. So at 0, is 42 less than 7? No. Is 42 less than 13? No. Is 42 less than 56? Yes, it is. So we're going to insert at index 2. So it'll become the new index 2. Everything after it has to shift down, right, to keep the order. And we break the loop. We come back. Do we have 5 numbers yet? No, not yet. Okay, let's get another number. What number? 35. Okay, we're not empty, so let's range through the length of lotto numbers. We have 4 numbers now. So we're going to get 0, 1, 2, and 3. Is it less than 7? No. Is it less than 13? No. Is it less than 42? Yes, it is. Let's insert at index 2. It becomes the new index 2. Everything else has to shift down. We break, loop's done. We have 5 numbers, program's done. So we built out this lotto ticket for them with numbers in order using insert. Kind of fun. Now, another, in case you were curious, sort of thing here. Let me change my lotto numbers here real quick. 5, 4, 3, 2, and 1. Print the lotto numbers. Lotto numbers dot. If you click dot, it tells you all the things you can do. Right? We've seen this in IntelliSense. There's one in here called sort. That's a whole lot easier, right, than trying to do that ourselves. There's a pain in the butt to do ourselves there, right? So if I just call sort, sorts them for me. But sometimes the order does matter, right? So depending on what we want to do with the list here, right? If we care what number your numbers were in, it matters. So, some lottos you have to match particular first number to first number, second number to second number, third number to third number. Some lottos just say if your number's in the ticket, great, because they don't allow duplicates in the winning numbers. Right? So if you think of the lottery like Powerball, they have a bucket of numbers they pull the first 5 numbers out of. There's no duplicates because they use the same bucket of 69 numbers to pull them out. So they get 5 out of 69 values, each with no repeats. So really it doesn't matter what order your ticket's in, right? Because there are no duplicates. So that sort of thing. So it's combinations, not permutations at that point, which is actually easier to win, right? If you're winning in combination, not permutation. Right? Otherwise, there's a lot more. So like, let's see, Wolfram Alpha is really good at this. So 69 combination 5 at a time means there are 11 million combinations or so of 5 numbers 1 to 69. And then there's the Powerball 1 to 26. So multiply that by 26, right, to get your chance of winning the jackpot, right? 26 times 111 million. We can do that math real quick, right? 26 times 1, 1, 2, 3, 8, 5, 1, 3. 1 in 292 million chance of winning Powerball. Again, lucky numbers aren't a thing. It literally doesn't. It's just not a thing. So no matter what ticket you buy, you have the same chance of winning the jackpot, which is 1 in 292 million. Okay. So at one point, the jackpot got up to like $1 billion or so. And someone was like, hey, if I was rich and had enough money, I would buy every single possible combination. And I'd be guaranteed to win. Well, one, you don't have time to buy 292 million tickets. Right? There's just not enough time physically possible to do that. Right? It doesn't work like that. And then 2, they cost $2 each. So you'd be spending $584 million on tickets to win $1 billion if no one else won. Because if someone else wins, you split that prize. And now half of $1 billion, and you've spent $584 million, you're out $84 million before paying any taxes. And if you win $1 billion, they're taking 39% of most of that winnings. And you don't even get all of it if you take a straight payout. You get like 2/3 of it if you want the straight payout with whatever the jackpot was. So the lottery is a tax on people who don't know any better, which is really unfortunate. But we instituted it anyway because people would go to other states and play the lottery there. Because sure, and yes, people are adults and can make their own choices, but it's a really bad tax on people who can't afford it. I don't have strong opinions about this at all. Sorry. Anyway, we're talking about lists. Go back to lists. So you can insert something. You can remove a particular value from a list. Remove by value. You can pop something off the end of the list, or you can pop a particular index out of the list. Right? We looked at lists and say, hey, do I have a value inside of it here? So let's take a look at, you say, hey, our index of 1 is going to be my lotto numbers dot index of 1. And this will either be the index it's at or -1. I think we did this one, right? Index to see if it's containing that value, right? So if my index of 1 is not -1, then we'll take my lotto numbers and we're going to remove, or no, let's pop the index, right? That's the longish way of saying lotto numbers dot remove 1, right? Get the index, and if it's there, remove it. If not, just remove it, that sort of thing. right? We can do that sort of thing. Let's remove it here, and it'll print a lot of numbers. Oh, we got to enter numbers. 1, 2, 3, 4, 5. Uh-oh. 1 is not in the list. What did I do wrong? Oh, not index. Sorry, index of 1. There we go. Index of 1. I used the wrong variable. Try that again. 1, 2, 3, 4, 5. Uh-oh, broke again. A lot of numbers. Oh, this one here. I'm sorry. 1's not in the list. 1 is not in the list. Didn't we add 1 to the list? I'm really confused now. A lot of numbers. Index 1. Huh. Index of the value. Isn't there a 1 in a lot of numbers? Oh, I've removed it. Folks, I'm really out of it right now. I did a marathon yesterday and got really sick. It was a rough day. Rough day. Yeah, so remove is bad. It doesn't work, right? So this is, I wouldn't even say that's safer. So usually you'd say like if 1 is in lotto numbers, then you could remove it, right? That sort of thing. Oh, no, I'm sorry. No, that's not even it. This index. Index is failing? Doesn't give me a -1? That's the wrong place. Just remove. I guess it fails. I really thought it would give you -1. Is that what just with strings? Index of? Now I'm surprised. That's okay. All right, yeah, so that just totally fails if it's not on the list. You don't even get the -1. So if 1 is in my lotto numbers, then go get it out, pop it out. Sure. Avoid a value error. There. So now it should run without errors. 1, 2, 3, 4, 5, and we get our list, right, without the 1. So again, remove is probably easier, but depending on what you're doing, if you want to get a particular index out, go for it. You can pop out a particular index. You can count how many times a value occurs. That one's fun. I think those are some basic lists. Right, iterating over a list, right? The 4 value in list we've done. Remember, you get copies of values, so we can't modify them. Usually we'd range over a list if we want to modify them. Enumerate is a fun little shortcut here. So if you want to enumerate a list, I could say for index and the value in enumerate of my in my lotto numbers. I could print, value is at index. I guess I have to keep typing my numbers here because I'm using lotto numbers. So we say it gets out both values at once. Remember we talked about this packing and unpacking that happens? I can get things back as a tuple automatically when I return things from functions. And I can just list out, comma separate, here's the values I want from that tuple. So you get both the index and the value at the same time. Now, it's not really a whole lot different than just looping over the range of the length here. In range of the length of lotto numbers. But then to get the value out, it's lotto numbers at index. So like you save a little bit of typing, I guess, and then it also gives you a copy of the value, right? This one is modifiable. So if you want to really make sure you don't change it by mistake, enumerate's nice because you have a copy. Just like a regular for loop gives you a copy of the values. I generally don't use enumerate, really because I just don't remember most of the time. Like for range and length is the most common, but it does the same thing, which is fun. So you can enumerate those particular ones. All and any are really fun. So you can say, hey, is there any value that is true in this list? Remember, 0 is false. Anything other than 0 is not false. And then all is saying everything is true rather than anything is true. So this is like more like an OR is index 0 true, or is index 2 true, or is index 3 true, or is index 4 true, or this one is index 0 true, and index 2 true, and index 3 true, and index 4, right? They all are true, or any of them is true for alls and any. You can get the min, you can get the max, you can get the sum. We've done those already, right? Min, max, and sum. Okay. Those are just more practice. Now, putting a list inside of a list. This is new, right? So this is where our head starts to hurt, but it gets really fun. So I can make a list here. I can make a tic-tac-toe board is a list of lists here, and I'm just going to give it, let's do some spaces here to get my tic-tac-toe board. So the first value in my list here is another list. So I have a list of lists. This is we commonly call these two-dimensional lists. Right? So the length of tic-tac-toe board, how many items does tic-tac-toe board have? Well, it has 1, it has 2, and it has 3. Right? So the length of tic-tac-toe board is 3. Each one of its items also has a length. So it's a 3 by 3 here. Right? So we can build out a list inside of a list. Now, they don't always have to be exactly the same, and you can do all sorts of crazy stuff with them. It's easy to start with squares. You could do rectangles, you could make really long ones, all sorts of other fun stuff with these two-dimensional lists. But they can work, right? So this is our tic-tac-toe board. Right? How about we figure out if the game is over? Right? Can we write a function for that? You know what? I think maybe we'll save that for lab. We'll do tic-tac-toe in lab with lists, and I think that'll be a lot of fun. We'll save that. I think that'll be a good lab exercise. We can make a tic-tac-toe game, right, using a list of lists, and then you can play tic-tac-toe. But you can put a list inside of a list. So to reference particular values, oh, they have tic-tac-toe over here. So the first value is the row, right? Give me the value at this index. Well, that's this entire row. If the other value there is another list, you can give it another index. Well, I want the index there. Sure, so that's row 0, index 0. Really, row 0, column 0, if you like to think of rows and columns. Now, the only downside is 0, 0 is the top left. This is not math land with an origin in the center. Right? 0, 0 is the first row, first column. That's your top left. So it's a little awkward for a while when we think about it in programming land with these two-dimensional spaces. Just pretend like math doesn't exist and there is no origin, and you'll do better. Otherwise, it's really confusing. Okay. So lists inside of lists. Sure, you can have a list of lists of lists. Holy cow, my head starts to hurt. This is a three-dimensional list. If you have to do a three-dimensional list, you've probably done a bad thing. There are other ways to solve problems that is not involving a list of lists. Maybe there's a case for this. You can make a list of lists and have like a 10th dimension and pretend that like you're learning physics. Because I don't understand how any of that stuff works. Go for it. I will not be able to understand any of it. And trying to solve a problem with a 10-dimensional list here is going to be pretty much impossible, right? We need to make sure we can solve a problem and it's understandable for us to break things down step by step by step by step. So maybe a third dimension, maybe. Hey, now I've got like a cube, and because we can like picture cubes. If you start to have a fourth dimension, I don't understand how that works. I can't picture that in my head, and I will just cry. Right? So yes, you can, but no, you shouldn't. And Python lets us do all sorts of really cool things, but we probably shouldn't. Okay. So to loop over individual values then, right, we could enumerate the two-dimensional list, then enumerate the individual row, and then get your row index, column index, all sorts of things here. So this list of lists here of currencies, sure. So for $1 to euros to British pounds, I feel like this is a little out of date here because the pound is in really sad shape, right? What is the conversion? 1 US to British pound? 0.88 now. Oh, all right, it's come back over earlier this month when it was at its like lowest time ever, right? Is that close to accurate now then? 0.65? Yeah, we are getting way more pounds to the dollar than we were before. That's a big change. Math is hard, friends. Math is really hard. Okay, so you can loop through. Again, enumerate's fine. If we make this list of lists here, if we wanted to just get individual values, we could say for row in my tic-tac-toe board. We could say for, if you say column in row, it sort of works, but I prefer item in row, just because it's not the like column index, it's the actual value in the row, the item in the row. I don't know if that makes much of a difference here. We could print the item. Now we're just going to get 9 blanks though, because we don't really have anything here. So if we made a tic-tac-toe board, who wants to play tic-tac-toe? We can play real quick. Then we can print out our board. That sound like fun? All right, who wants to go first? I guarantee you guys won't beat me. It's not a very exciting game. Just shout out a spot. Where are you going to move? Top right. Okay. I'm going to go in the middle then. Bottom left. Oh, goodness. So I think I have to go in the middle then, right? Okay. I think you go here to block me. I go here to block you. You go here to block me. I go here to block you. And all you have left is here. Cat's game. It's a very exciting game. But if I just print, right, and leave the default new line character here, it's not going to look very nice. No, run selected. I clicked the wrong button. Right, we get 1 item per line. That's not very useful here, right? Trying to loop through, because in this case, like, it matters that they're an individual row, right? If we just wanted to print the row, it actually turns out not too bad here to just print the row out. Right, that's not the worst looking thing in the world. If you don't want the square braces, though, right, we got some options. So if I don't want the square braces, I need to get the individual items here. So then I can say for item in row, and then what I would want to do is I want to print the item, and I want the ending character to be a space, to kind of space separate them a little bit here. And then when I'm done printing each item in the row, I'm going to print just a new line just to go down the line. Right? So print each individual item with space separators. Or really, you know, we could, we've done the joining now, so we can say print the space joining the row. Probably a little nicer, and then we don't have that trailing end. And then we automatically get the new lines with a regular print and not changing the ends here. So that's probably a little nicer for us. And now we get more of a nice looking board here. Sort of, right? Sort of. Or if we wanted, we could print, instead of a space here, we could print a pipe character, a vertical pipe. We could print the row, and then we could print a bunch of dashes here. I think it's 3, 4, 5 dashes. 1, 2, 3, 4, 5. 5 dashes after each row. Right, if we print that one. Oh, I've got an ending one. Oops. I don't want the last one. How do we not do it on the last one? So we probably need the index. That's a bummer. Index in range, length of the tic-tac-toe board. We're going to join the tic-tac-toe board at index to get that, and then we can say if index is less than 2, print it. Right, when index is 2, don't print it. We don't want the last one here, right? Just to make that print out a little bit nicer here, because we got a pretty looking tic-tac-toe board. Look, now we have a nice looking tic-tac-toe board. Does that look much nicer? You aren't impressed. I'm sorry. You guys bored? It's Monday. Mondays are hard. Okay, but you can loop through getting individual rows out by index if you want, or get the individual. So we just did this to make it print nicer. We could have also used enumerate if we wanted and got the individual row and the index value. That would have made this typing a little bit easier maybe. If we wanted to enumerate, we could say index and the row in enumerate the board, enumerate, right? We could get now just the row, and then we can still check the index, right? I don't know if that was actually less typing because like this took longer to type, but it does the same thing for us. Do you want both versions? I'm sorry. Let me undo that. That one, and then here's the other version with enumerate, right? Should do the same thing if we did it right. Yeah, and we get out 2 tic-tac-toe boards. I guess we should have some prints in between, right? Just print, oh goodness. Print. Okay, just put some prints in between. Run our tic-tac-toe board again. There, now there's some spaces. So enumerate, or just with index and range length. Same thing, gets the job done for us. That's with a 2-dimensional list. We did list slicing already. Oh, so we did string slicing, I'm sorry. You can slice a list the same way you can slice a string. Right? Give it the start index, give it the end index, give it a stride. Works out the exact same way it does with strings. Remember, strings were sequence types. Lists are sequence types. So tell me what index you want, tell me what index you want to end at, and if you want to give me a stride, go for it. It defaults to 1. So works out the same way. What is nice about this now, though, is I can write a function. So if I write a function for, I don't know, add value to list, given some list here, and I take some list and I want to append 42 to it. So if I have, I don't know, my lotto, sure, let's just make a new list here. So some numbers is a list of like 10 and 20. And I call add value to list given some numbers, right? And I print some numbers. What's going to happen? We're going to add 42 to it. And then when we're done, it'll still be there because we gave it the list. When you give a function a list, it can't change the list in memory. It can't say point to a new list in memory. But the function can say, hey, go and add something, go and take something away. You can modify the list. Right? Functions can modify lists. So when I go and run it, now I'll get the 42 in there. Remember, when you took a slice of a string, you got a copy of it. So if you want to give a copy, of your list to a function, slice it. This is our shortcut. So if I want to give it a copy so it can't change it, I will slice from beginning to end. If I slice from beginning to end, it gets a copy of all of the items in my list. Now when I run this, it adds a 42 to the copy that it had. The copy that it has goes away when this function is done, right? So it's no longer in scope. This variable doesn't exist anymore. We're going to go get rid of it, give the memory back to the operating system. So, hey, Python, tell the operating system we don't need it anymore. So some list only exists while this function is running, and then it goes away. Because some numbers we made a copy of to turn into some list. We still have some numbers, the original. Does that make sense? Okay, cool. So slicing is really handy for making copies. Right, looping over modifying lists, we can do all that. Done those ones before. List comprehensions are some of the weirdest things. This is shorthand notation because people are always wanting to write less, right? Good programmers are lazy. If you do enough of these, they start to make sense. Otherwise, they're just crazy. So you can make a new list out of an existing list or out of an existing collection with this backwards notation. So for every I in my list, get I plus 5. Turn it into a new list called list plus 5. Right? So it works the exact same way as doing it the slow way. So if I have my some numbers here, right, and I wanted to say, here's my new numbers equals a list, and I wanted to say for number in some numbers. I'll take my new numbers, and I'm going to append a number plus 5. Right? It takes 3 lines and turns it into 1 line. You'd say more new numbers is a list, but inside of that, we're going to give it a comprehension. We're going to say number plus 5. And this, you write it totally backwards here, which is crazy. For number in some numbers. So you write the for after you write the what you would have done inside the loop. You don't write the loop and then the thing after. These ones always confuse me. But if you do them enough, they start to make a little bit of sense. And it's a handy shortcut. You'll see a lot of people do this because we like writing things in 1 line instead of 3. But these do the exact same thing. Right? It does this loop. And then for every item in that loop, we do this thing here, putting it inside of a new list. Just like making a new list, looping through it, doing something with it, adding it onto the list. Right, so when we're done, if I wanted to print new numbers and I wanted to print more new numbers, we should get 15 and 25, right? Want some numbers. Oh, I need that one too, sorry. Right, both versions give me 15 and 25. So it's just whichever one you prefer. So this is the list comprehension. Right, so you get the loop part here, and then you get the body of the loop on this side. The other crazy thing you can do with list comprehensions is you can add conditions. So kind of fun, or you can do other arithmetic with it. So like take a list of numbers, turn them into strings here. Sure, that's kind of fun. You can split out your input in line of a for input in the split of input, turn them into integers. This one's kind of fun. You can take the sum of each row in a 2-dimensional list, turn it into a list of sums. Sure. Yeah, so they're showing you the slow way and the quote fast way, right? The original way you would have done this versus the list comprehension way, right? The minimum of things. The conditional. You don't put the if on your expression, you put the if after. These just start to get nuts, and it's okay. Just go look it up because that's what you have to do for a while. So the loop is still in the middle. The condition goes on the right-hand side. The expression is still on the left-hand side. So if I wanted to add 5 to a number, if it was less than something else, right? If I had like a bunch of scores, I'm going to say, hey, let's just bump everyone's score. If they don't already have an A, let's give them more points. We'll say scores is what, like 70, 80, 90, 100 or so. And how about we get an average, right? So we get an average score is the sum of scores divided by the length of scores. And then we'll say new scores is a list, and for score in scores, if the score is less than the average score, we'll take my new scores equals the score plus 5. We'll just give you a 5 bump here, right? We could do it in 4 lines now. If you don't want to do it in 4 lines, you can do a list comprehension, right? You could say more new scores here again. I'll just do that. More new scores is a list of what? Now, I usually try and write them in order, and that helps me make a little bit more sense of this. I'm going to say for score in scores, what? If the score is less than the average score, then what do I want to do? Now I come back and say, oh, hey, I want the score plus 5. It's not always the right way to write it, but to me that makes a little bit more sense to try and follow along with these, right? We get our loop, we get the condition, then we get the expression. What are we doing with it? Right, when we're done, we can print new scores, and we can print more new scores. Should work exactly the same. Oh, new scores. No, it doesn't equal. We want to append. Oh my goodness. New scores. Append Score plus 5. You folks, you gotta catch me when I do dumb things, because I'm a little tired. We didn't get all the values out. That didn't work right. We got the values if the score was less. I didn't get the unmodified values here, right? I was only getting the ones that didn't have great scores. But, you know, it didn't work in this first one either, so that's probably okay. We could go and be better to just loop through, right? Not build a whole new list, right? So these, I don't know, low scores with bumps or something. We just get the 75 and 80. The scores that were less than the average, added 5. There's a lot of people like a kind of shortcut here. If you have, I don't know, we had our like some numbers. I think we still have some numbers, right? Yeah, some numbers were like 10 and 20, or we bumped them up to 15 or something. So if you want to get even numbers, right, a quick list comprehension is just the number, right, for number in some list if number modulus 2 is 0. Right? If I can evenly divide out 2, there's no remainder, it's an even number, this will give me just the even numbers. It's a pretty quick way to get that, right? So some list is a list of a range of 10. So you can take ranges. So ranges themselves aren't lists, which is kind of weird. But I think we can loop through. Yeah, so we can't. Okay, so we can take a range here. It's not really a list, but it's close enough for our purposes here, making a new list. So it'll give us all the evens. We could get all the odds, right? Just saying if it equals 1, or if it's not 0, it's true. So you'll see a lot of times people do odd numbers is just saying mod 2. Because if it is 0, it's false. Because 0 is considered false in Python. Right? 0 is false. Right? So you see that a lot too. That's a pretty common shortcut. Okay. So that's list comprehensions. Those are a lot of fun. Sorting lists. So we looked at the .sort function real quick. I told you there's a shortcut here. So sort will modify the list. There's also another version called sorted. Sorted gives you a new list that is sorted of the original, right? Like slicing gives you a copy, sorted gives you a copy. So I would say, you know, a new list is sorted version of some numbers, right? So sorted gives a copy, right? It doesn't change the original. So if you don't want to change your original order, but you want a sorted version, you can use sorted to give you a new version, right? Back when we did sort, I think it was at the top, right? Here, I just said lotto numbers dot sort. I didn't have to say lotto numbers equals lotto numbers dot sort. I didn't have to reassign anything because sort just modifies the list. The list in place. Right? It actually changes the list you're asking to sort. Where sorted doesn't do that. Sorted gives you a new version of it here. Okay. This is not all that interesting. You can read about that later. And then dictionary. Okay, so we're going to save dictionaries for Wednesday. So we'll do our lab coming up in a little bit. We're going to play our Tic Tac Toe game. So we're going to take this and we're going to break it down into functions. Right? We'll take a big problem and make it in smaller and smaller and smaller and smaller pieces here. So I can solve small pieces. Like, is the game over? That's a small piece. Well, you can actually break that up into even smaller pieces. That's, is there a tie game, or did someone win? Right? So we can break that up. Did someone win? Is it a tie game? Those are both part of, is the game over? And then we can loop real quick and say, okay, as long as the game's not over, let's keep on going. And then you can ask, hey, where does X go? Where does O go? Right? And just have them drop pieces in given locations. Kind of fun. We'll build out tic-tac-toe, have some fun with a list of lists. Okay? All right, you got anything else? Cool. I will see you folks over in lab then in a little bit. Thanks, everybody.